graduated from Oxford. So
Okay.
go ahead.
Thank you. Apologies for the delay at the beginning. It seems my computer decided to be uncooperative, so I'll try to speed up during this talk, which is work that I have done with Margarida Tello de Gama, who is sitting over there at the University of Lisbon. And what we are going to be talking about is the switching of a filled state on a patterned surface. This is a nematic. So our motivation is that we know in wetting theory that if a surface is topographically structured, then the configuration, the wetting configuration, can be filled, not completely wet and not completely dry, so that there is a thick layer that fills the structure with an interface pinned on the features of the structure. Now, when this fluid is a nematic liquid crystal in coexistence with its isotropic phase, then the nematic order allows for multiple metastable states to exist, distinguished by the texture of the nematic and the profile that the interface makes. And we also know that electric fields couple to nematic order, and this may cause transitions between these field states, and such switching offers a means to control the shape of the interface, and this may be useful for microfluidic or optical applications, possibly also for colloidal self-assembly. So we model our nematic liquid crystal using a Landau-de Gennes free energy in the Q-tensor formalism. You've probably seen this or something like it before, but we have various contributions to the free energy, including the bulk terms, elastic terms, electric terms, and a wetting term. And the bulk contribution may be written in a variety of ways. Here we write it so that we express it in terms of the nematic phase, the degree of nematic order, and in terms of a temperature-like parameter which controls which of the states is favoured by the system. And if we choose the temperature parameter to be 1, then we have coexistence between the nematic phase with nematic order in S nematic and the isotropic phase with 0 nematic order. The elastic contribution can have 3 terms up to quadratic order in Q, although in the bulk these two are actually indistinguishable and they only integrate to a difference at the surface. These different coefficients allow you to tune to some extent the Frank elastic constants of your bulk nematic. But the reason we're more interested in them here is because they also allow us to tune the surface tension of the interface between the nematic and its isotropic phase. And as you can see, we have different surface tensions depending on whether the orientation at the interface is perpendicular or parallel, and also the interface has a characteristic width known as the correlation length that depends on these elastic coefficients. Interaction with the electric fields. We know, of course, that there is a dielectric term proportional to Q, but for this study here, we're not going to pay attention to this. We're going to assume that this anisotropy is small compared to the isotropic part. And what we're more interested in are the flexo-electric and order-electric terms. And we know that a nematic liquid crystal, an apolar nematic, cannot be ferroelectric because there is no polar order, but gradients in the apolar order do permit a polarization which will then couple with an electric field, and there are actually 4 independent terms up to quadratic order in the coefficients. And finally we have a wetting energy. So what does this look like? And quickly, we solve the system using the lattice-Boltzmann finite difference algorithm, but I'll just skip through this because we're short on time. And this is the system we're looking at. It's a system made of rectangular grooves. The anchoring is homeotropic, perpendicular anchoring. The anchoring of these are the dimensions. The anchoring of the interface is planar by choice of the elastic coefficient. So straight away we have a conflict between the interface and the walls, which leads to interesting shapes of interface. And these are the states that are found. These were actually found by our colleagues in Lisbon. And there are 3 textures that occur in the groove. A state with a bend distortion at both lower corners, a state with a bend distortion at one lower corner and a splay in the other, and a state with splay distortions in both lower corners. And also the upper surface of the substrate can either be dry or wet. So that gives us 6 states altogether. These are all metastable states. This one is actually the lowest free energy, but all of these for the parameters that we're using are metastable. So we look and see how the electric fields may switch between the states. And these are the polarizations under each of the 4 coefficients that I showed earlier for each of the states. And what we concentrate on first is the order electric polarization, which is just a polarization of gradients in nematic order, ignoring any orientational configuration of the nematic. And what happens in this case, if this is the dominant type of coupling, is that the application of a field can cause an interface to either grow or shrink on the upper substrate of the surface, while leaving the texture within the groove relatively unchanged. But if we apply this in the field in a horizontal direction, in an attempt to switch between textures in the groove, then we see that this substrate here will only de-wet, but there will not be any change in the actual distortion in the corner, and therefore it's not a means of changing between textures. But what is, if we return to the polarizations, is actually this this term here, this term which is the difference of bend and splay terms. And the reason is that the flexoelectric polarization in the corners is of opposite directions depending on whether the distortion is of a bend or a splay variety. If it's a bend, it points out of the corners. If it's a splay, then it points into the corners. And we see that by applying an electric field in a downwards right direction, we are actually opposing the outward polarization at this corner here and causing this region here to shrink. And the interface then moves to the lower corner. And once it does that, it easily rotates under the influence of the electric field, re-wets the wall, and then we are left in a state with bend in one corner and splay in the other. And by applying an electric field in the upwards left direction, we can actually reverse this transition, because now this field is opposing the splay configuration in this lower corner and induces the director to rotate until we're back to a bend in both corners. And there are some other transitions that can be done. For example, a transition to the splay. But seeing as we're out of time, I'll just talk about the directions that we want to take this work in. So we need to look more carefully at the exact details of the electric field, because here we've assumed that the electric field is constant, and what we need to do for a more thorough treatment is to solve Maxwell's equations taking account of the flexo-electric self-polarization, the dielectric anisotropy, differences in the dielectric coefficient between the substrate and the fluid, and looking at placing electrodes within the system rather than just applying an external electric field. We want to look at a 3D treatment because although this system is translationally invariant along the groove, the flexo-electric coupling may induce variation along the groove. We want to look at temperature-driven transitions because the difference in interface between these states means that they have different volumes of nematic, and therefore raising or lowering the temperature will likely change which state is favoured. And finally, we want to look at using substrates like this as a template for the assembly of colloidal particles. So this work, these are other people whose input was very helpful to the work, and the Portuguese Science Foundation funded the work, and I'd like to thank you for your attention. Thank you.
We have time for a couple of questions still, please.
I would advise to add to future consideration disclinations, because you consider only smooth deformations, but might be it's much more easy not to deform orientation, just create dislocations on number of dislocations.
We haven't seen any dislocations forming under the application of electric fields, although it's possible that applying an electric field into or out of the plane may cause the director to escape into the third dimension. Yes.
At the beginning, you related the L1, L2, and L3 to the surface
Yes.
surface tension. What's the basis of that calculation?
The basis.
Formula, whatever.
Um,
Like the gamma.
we worked it out using the uniaxial approximation, and then you find that with L1 there is only a square gradient term in S, the nematic order, but with L2 and L3 there is a term which has dot products between the director and the surface normal, and the gradient of S.
And the A comes in?
The A comes in because we want to minimize the sum of the bulk and elastic, and that gives a trade-off which sets your width.
It's a sort of natural boundary condition. You may, in principle, to add something external surface.
Sorry, external.
Your contribution, gamma parallel, gamma perpendicular,
Yes.
what comes from the bulk, it's natural boundary condition.
There is no boundary condition.
Elastic energy and
Yes,
coefficients.
there is
But
no.
might be something additional surface energy just due to interface with air or with substrate.
I should clarify. These are not boundary conditions.
Yeah.
These are.
It's what I said.
Yes,
It's
yes.
natural boundary
Yes,
condition
yes.
which comes from the bulk.
Yes, that's right. Yes, it's a diffusing.
But in
space,
real
yes.
system, you could have some additional boundary conditions due to interface with substrate or with air.
Yes, but we do also have the wetting term, which is also very important. This is the interaction with the substrate. If we wanted to discuss a free surface, then what we would need to do is put in another order parameter, a binary phi parameter, and then couple the nematic and isotropic to that, and that would give us more freedom.
Your wetting term has something to do with orientation only, but
Yes.
I said it's related to surface tension. There is surface tension just proportional to area, not to...
Yes, so that comes naturally out of the treatment. Yes, these are the effective surface tensions.
Okay, we can continue later. Thank
Yes.
you very much.
Thank you.